Bismillahirrahmanirrahim. In today's video, we discuss about the analysis of the conversion ratio MD. So now, as we know that the conversion ratio MD is equal to V naught by Vg, and we also derived it for buck converter, in which MD is equal to D. Now here we derive it again for buck converter, but for DCM. So now let's draw the graph for buck converter. So this is the graph for buck converter. This is Vg and this is V. This is C, this is L, this is diode current ID, this is MOSFET Q. Now here we apply the same method as we previous, that is the volt second balance and the current second balance. Now as it is DCM, so the small ripple, let's see to the small ripple approximation, that either that apply here or not. If yes, then how we apply that small ripple approximation? Now as we know that in inductor the DC voltage must be equal to 0, because when, as we know that when the current flowing and DC current flowing in inductor, then the voltage across the inductor is equal to 0. So now for this we take the average value, as average value is equal to the DC value of the inductor voltage. So that will be equal to 1 by Ts VLT into dt, and that must be equal to 0 as we applied already in smart ripple approximation. Now here for capacitor we see to the current that the current must be equal to 0 TSICT into dt is equal to 0. So now let's see to the linear ripple approximation and the output capacitor voltage ripple. Let's see to the output capacitor ripple voltage ripple. So now the current in DC current in capacitor is equal to 0, so the voltage at the output must be equal to the capacitor voltage and resistor voltage are equal. So in DCM the condition must be that the ripple in this voltage must be smaller than the DC voltage of this, that is the ripple in this voltage or capacitor voltage must be smaller than the DC voltage. So we can say that in capacitor the only DC voltage present. Across it, as we know that in output voltage contain the DC voltage plus the AC voltage. So now we say that this AC voltage is equal to 0, so the net voltage will be equal to DC voltage. So you can approximate your output voltage is equal to the DC voltage according to a smart ripple approximation. Now let's see to the inductor current ripple. As we know that I already discussed in my previous video that in DCM the inductor current ripple is greater than the DC current flowing across the inductor. So here the small ripple approximation is unable to applied because of the DCM, or according to this condition which the DCM circuit obey. So that's why we not apply that small ripple approximation, or not equalize that small ripple approximation to the DC current. In DCM, the inductor current ripple is not very smaller than the output DC current, so that's why we not neglecting that and unable to equalize that equal to the DC current. So that's why if we equalize it to the DC current, then that will lead to the incorrect result. So now let's do analysis for DTS, D1TS. So for D1TS, the circuit will become like this is the source voltage, and this is the inductor L, and this is the capacitor, and this is the resistor, this is the output voltage. So now do the analysis. So for this VL, T will be equal to Vg T minus V naught T. So small ripple approximation will be equal to Pg minus V. This is equation 1. Now the current will be equal to ILT will be equal to ICT plus I T output current. So the capacitor current will be equal to ILT plus this also equal to V by R. So after small ripple approximation, we say that this is smaller, not converting to higher, as I already discussed. So this is equation 2. Now we for D2TS, the circuit become plus minus VCL. So VL become equal to minus V naught. After small ripple approximation, I directly applied small ripple approximation, and IC will be equal to V by R minus V by R. Plus I L to T. This is smaller, not in capital. So care must be taken in citing such type of equation. So this is equation 3 and this is equation 4. So now apply, and the third also second most also the for D3TS, as we know that in inductor current ripple IL, for DCM it is such like this is D1, this is D2TS, this is D3TS. So now for D3TS, as we know that the voltage across the inductor is equal to 0, so the current will also be equal to 0. Why the voltage across inductor is 0? Because we know that VL is equal to L di by dt. So here the slope is equal to 0, so VL also equal to 0. So, and the capacitor current IC T is equal to I L T minus V T divided by R. So in here this is equal to 0, so IC will be equal to minus Vt divided by R. And the second most important thing is that here sometime the ringing come, such type of ringing come. Why these come? This is because here the resonance between inductor and capacitor occur. As these two are in parallel, so therefore these two resonate at some frequency, and that resonate result in a ringing, and that ringing we can see through oscilloscope in the form of this much. But this is too small, so we neglect this ringing. So now apply volt-second balance. So after applying volt-second balance, VLT is equal to the first equation, which is VGT minus V. So the D1, we have VG minus V, and D2 we have minus V0, and D3 we have VL is equal to 0, so it becomes equal to 0. So from this we get VG D1 minus V D1 plus minus V0 D. So that will be equal to 0 is equal to VG D1 minus V D1 plus D2. So the conversion ratio will be equal to D1 by D1 plus D2. So here let's see to the conversion ratio. In this ratio, D1 we already know, because we set it by our own self, that whatever I want, I set that by my own choice. But unable to know about D2, because I don't know that at up to which time it de-energize. Up to which time I know that I give this much of time for energizing, and I already know that in CCM the other time, which is 1 minus t, the inductor fully de-energize. But in DCM I know that I give this much of time for energizing the inductor, but don't know that at which time it become fully de-energized. So I don't know this boundary condition. So in order to find this boundary condition, I apply the ampere-second balance. So in that case, and that ampere-second balance will be little bit different, because here the inductor current ripple is not equal to 0. So we see two things here in this ampere-second balance. One is I peak, and I peak is this. The second thing is the area under the curve. So these two things are very much important. So let's see to the I peak. The I peak will be equal to the slope into time. So I peak will be equal to slope for this is V minus Vg divided by L, and the time is d1 ds. So this is the IP, I find this IP. Now as we know that the inductor current, average inductor current is equal to DC current, and that is equal to 1 by Ts 0 to Ts IL dt. So after applying that, we get Ts IL T, that is the area under the curve. So area under the curve, as we know that, and area under the curve is equal to 1 by 2 base into height. So here the base is d1 plus d2, so that will be equal to 1 by 2 d1 plus d2 into height is IP. So putting this value into and the Ts, so that Ts is here. So now putting or do substitution of equation 1 and 2, so we get 1 by 2 d1 plus d2 into IP. IP is equal to 1 by Ts. Now we putting this value here, so we get IL, average DC value of the inductor, is equal to this, as this is equal to this. So this, instead of this, I can put by 2 d1 plus d2. So the peak value is that V minus Vg divided by L into d1 Ts. So now according to the relation that the DC current, this is the DC current which is flowing in resistor output load, and that is equal to V by R. The DC current or the average value of the inductor current is equal to 1 by 2 d1 plus d2 V minus Vg divided by L d1 Ts. So now simplifying it, d2 Vg, take common Vg, so it will be equal to so here again we do a mistake, and that mistake is this, is Vg minus V0, because it is the buck converter, and in buck converter the input voltage is higher than the output voltage, so it's equal to Vg minus V0. So it's become equal to 1 minus V0 by Vg d1 Ts. So let's V by Vg is equal to X. So this Vg have come here, so it's become equal to V0 by Vg, and 1 by 2 d1 plus d2 into 1 minus V0 by Vg to d1 or Ts. So now putting this equation, so it's become equal to X is equal to 1 by 2 d1 plus d2 to 1 minus X d1 or Ts. So the equation become equal to X is equal to 1 by 2 d1 plus d2 1 minus X d1 plus d2 1 minus X d1 r Ts. As we already know that from volt second balance that V naught by Vg is equal to d1 by 1 plus d2. So here it will be equal to x d1 by d1 plus d2. So d1 plus d2 is equal to d1 by x. So put this value here, so we get x 1 by 2 d1 by x 1 minus x d1 ds. So it will be equal to it's become equal to d1 square into 1 minus x divided by x into 2L by R Ts is equal to tau, 2L by R equal to K d1 is the equation become equal to d1 square by k minus d1 square by k x. So it will be equal to x square plus d1 square by k x minus d1 square by k equal to 0. This is equation 6. So now simplify it by using this minus b plus minus b square 4ac divided by 2a. So simplifying it, putting d1 square by k minus d1 by k whole square minus 4 d1 square by k divided by 2. So from it you get, simplify it, you get the value 2 by 1 plus 1 plus 4 k by d1 square under the root. So this is the final equation for it. So now where the k is equal to 2L by R Ts or 2 ta by Ts. Okay, and now this is applicable for DCM, and in DCM we know that the k is less than k critical. So care must be taken in doing such type of equation. So now for CCM we know that k is greater than k critical. So we get such type like conversion ratio that MD is equal to D for k greater than k critical and equal to 2 like this. MD is equal to D for k critical and equal to 4k by d1 square under root for k less than k critical. So now let's draw the graph. This straight line come for k greater than k critical, and this is in sphere, so such line graph come for k less than k critical. And if you minimize the k further, so you get this line. If you minimize the k further,